Counting is one of those things that's everywhere, but you don't notice it until someone points it out to you. So that's what's going to happen here is I'm going to show you a situation where counting occurs that you might not expect, and then there are all kinds of rabbit holes to go down, which we're not going to go down all of them, but we're going to look at this counting problem two different ways and come up with two different very pleasant surprises or useful strategies from this at the end. So the problem that we're going to look at is something that you would have done in high school algebra, but we're going to look at it now as a counting problem. I said counting's everywhere, and the simple high school algebra problem really is a counting problem, but we don't tell you that when you're in ninth grade or whatever. So what we're going to look at are the powers of a sum. So I'm going to take two arbitrary things, I'm going to call them a plus b, and I'm going to raise them to some power. And we want to see what the pattern is. This is something that you could easily compute, but you miss out on the pattern. So that's the problem that we're looking at, something that you would have done in high school algebra. And what we're going to do in order to look for patterns, and you know, computer science is the study of patterns. So this is very consistent with doing computer science. The first one, I'll keep a note of where we are. The first one is a plus b. A plus b to the 1 is just a plus b. That's one of the standard exponent laws. Not very exciting, I admit, so let's keep moving on. Let's look at the square of a plus b. So that's a plus b to the second power. And you probably have this memorized as a squared plus 2ab plus b squared. Let's get on with our lives. But in fact, we're going to break this down and see how it got done. So I'm going to start with a plus b quantity squared, as we used to say. And I'm going to say, well, actually, let's break that down to what we really mean by it, which is a plus b times a plus b. And now I'm going to use the distributive law. So this is a times a plus b times a plus b. And I'm going to be very literal about this. I'm not going to allow myself to do any simplification. You always have to organize before you calculate. That's especially true in computing. No, it's especially true in mathematics. No, it's especially true in accounting. Whenever you're calculating, you need to make sure that you're doing the right calculation, which means you have to be organized first. So I have broken down the idea of squaring into very, very elementary in the sense of periodic table of the elements steps. And now I'm going to be super literal about this, and I'm going to say, well, what we have is a times a. I know you want to say a squared, but if you want to look for the pattern, you don't simplify. And then we have a times b, and then we have b times a, and then we have b times b. This is very literally moving blocks around, cut and paste. And there's something very, very important to notice about this, because what I've done is made it like the order matters. This is now a choice that we've made, and you have A, then B, or you have B, then A. So that's completely consistent with we've been talking about as far as counting. And so there's the situation. There are all the permutations of a set with two elements. If the elements are A and B, well, they're the permutations of the order. Now, we usually think of this as being multiplication, but when we're looking for patterns, we don't multiply. And so there's our situation. And I'm going to make a note that I'm using an alternative notation. So let me note that as well. We've been calling this P21, but this is 2 choose 1. And so how many ways can you choose one thing out of a set with two elements? And what we do is choose where the A goes. Okay, so that was fun. Now let's move ourselves up to n equals 3. And so that's a plus b cubed. And now I want to emphasize something that goes on because, again, we're looking for the pattern. Well, first of all, this is a plus b times what was above. And I'm not going to, I can't do copy and paste on paper. So I'm just going to indicate in green what was above and bring it on down. So that's what we had before. Oh, I did the wrong one. Screaming sacks of used macaroni. Okay. There. This expression with 4 terms goes in here. And so what we're going to end up with, well, we're not ending up, we're right in the middle. But for the moment, what we're going to end up with is a times the green thing plus b times the green thing. And so this is a very interesting step because the green thing had 4 terms. Now we have a times each of those 4 terms and b times each of those 4 terms. So in fact, the number of raw terms, the things that you do before you multiply it out and say, oh, that's a to the 7th times b to the 4th, the number of raw terms doubles at each step. You get a times the old ones plus b times the old ones. So this is an important pattern to make a note of. And so I will put a note in here, is the number of raw terms, not simplified at all, doubles each step. So that's actually a pretty exciting thing. And this is the kind of thinking that one needs to do if you're working with these kinds of discrete structures. Okay. Well, we're going to simplify that as well. And so let me just kind of, well, let's see what happens here first of all. So let me copy down the green thing. I need my green pen for the green thing. And that is AA plus AB plus BA plus BB. And again, this is AA plus AB plus BA plus BB. That's just a cut and paste operation. When this was invented, they didn't have cut and paste. Well, they did. But now we can take advantage of cut and paste. And let me write out what the new terms are. And the new terms are, well, it's just, there are going to be 8 of them. So it's AAA plus AAB plus ABA plus ABB. It's easier if you sing it. Plus BAA plus BAB plus BBA plus B, the B, not the B, B. Woof, 8 terms. And there are some patterns to this. That's why we're here. And, well, we've got the A cubed and the B cubed. That's just, we'd expect that. I mean, AAA, BBB. But the other situation is the other terms either have 1A or 2A's. So let me kind of group those. So here are the 2A terms. They're in green. And here are the 1A terms. They're in red. And so we'll just make a note here, 1A and 2A's. I'm not sure whether that needs an apostrophe, but let's put it there anyway. So I've taken the 8 terms, grouped them by using the pattern, and the pattern has nothing to do with the arithmetic. It's just, oh, there's 2 A's here, there's 1 A here. So this is actually a general counting problem that is applied to this algebra situation. So what we're trying to do is, well, we knew the algebra, so we're trying to back off and find the general counting situation. And if you go back and look, there it's tempting to say, hey, look, there are 3 green ones and 3 red ones. Too bad they're not M&Ms. Anyway, there are 3 green ones and 3 red ones. That's wrong. It's the right number, but it's the wrong computation. Organize, then calculate. And so for the A ones, what we're seeing here is we've got 3 slots, because everything's degree 3, and we're picking where do the 2 A's go. That's a counting problem, and so we know the answer is 3 choose 2. 3 slots, where do you put the 2 A's? And for the red ones, those have 1 A, and so the answer of how many terms are there is 3 choose 1. Now, if you calculate these out, that's 3, that's 3. So it's tempting to go straight to 3, but you miss the pattern. So there's the pattern. And I'm going to jump ahead a little bit and reach my conclusion, which is for the general n, a plus b to the n goes as follows. You have a to the n, and then the next term is going to be, everything has to be degree n here. So the next term is going to be n choose 1, a to the n minus 1, b to the 1. And then n choose 2. Let me do a couple here so you can see the pattern when I hold it up. A to the n minus 2, b to the 2. So what we're saying here, I'm not done yet, excuse me. What we're saying here is there are n factors, and one of them is b, and the rest, well, that would be n minus one of them, are a's. And then we have n choose 1 spots. Where does the b go? And then we've got n factors. Now 2 of them are b's, and n minus 2 of them are a's. And we have n choose 2 choices as to where do the b's go. So I guess we can use a little hive mind mentality here. Okay, honey, sorry. So we continue on this pattern, and the general term is n choose k, a to the n minus k, b to the k. And it looks like I'm going to have to go down onto the next line. So now k of them are b's, and where do they go in terms of this kind of analysis? They're all going to end up having the same thing when you multiply, because multiplication is commutative, but there are different patterns that go into that. We need to count how many ways that went into it. So the final situation that we get here is we're going to get down to, I didn't bother to write it down, so this is going to be n choose n minus 1, b to the n minus 1 times a, plus n choose n, b to the n, and just to be pedantic, I'm going to write a to the 0. So we always have 2 things that add up to a. Okay. So that's the general pattern. So these numbers, these number of choices that you have, how many ways can I fit k things into n slots, where n's bigger than k, comes down to actually comes down to this counting principle, and this is the number of things that you see in a binomial. Okay, fun surprise number 1. 2 to the n. Okay, now we're going to get down drilling really deep into the arithmetic. 2 is 1 plus 1. So 2 to the n is 1 plus 1 to the n. This is how a lot of discoveries are made, is you unsimplify, you break things back up, not down, and say, hey, 2 is 1 plus 1. And now I have 2 terms, a 1 and a 1, yeah. And I'm raising that sum to the nth power. Well, that's what we just did right here. And so when we raise that sum to the nth power, what we're going to see is the sum, n choose 0, plus n times 1, plus, n choose 1. I said times, I meant choose, plus n choose 2, all the way down to n chooses n. So that means that if you add these all up, oh, I forgot to say the 1 to the k and the 1 to the n minus k. But when we multiply by 1. That doesn't change anything. So when we add up all of these binomial coefficients, we get 2 to the n. So this is an unexpected pattern. And I'll tell you something. If you're interested in computing and someone comes up to you in the street and says, power of 2, you go, oh, tell me more. So that's an important thing in computing. Okay, so now we're going to come up with surprise number 2. That was surprise number 1, is that you have an alternative way of calculating 2 to the n. And that's not the only way of calculating 2 to the n. This is just one of the ways that shows the connection with various kinds of counting. The other situation here is if we go back to this step, where we take everything that was above and we multiply it by a, and we take everything that was above and we multiply it by b, and now we're actually multiplying. So what we have here is at step n, so we're doing this in an iterative manner. At step n, you have the powers that you see are a, I'm sorry, I'm saying the wrong step number. Let's try this again. I have a times a to the m minus 1 times b to the n. That's one way to get an a to the m, b to the n. And the other way is to take a b times a to the m, b to the n minus 1. So these are two different ways to get a to the m times b to the n. So as we go through this step up here, what we're seeing coming down on the next line is the contribution. There are two contributions. And so there's a nice way to arrange this, and I'm going to start with, and we're just writing the coefficients. So the first coefficient is 1. That's a plus b to the 0. Then 1, 1. And now I'm going to give you the 1, 2, 1. We've evaluated things. And here's what happens. Where did this 2 come from? This 2 came from that's the AB terms. Well, that was a times b or b times a. And so that came from a times the one before or b times the one before. And so I'm going to draw that in this way. When I do a couple more, that pattern will become more obvious. The next one, we knew the coefficients were 1, 3, 3, 1. I'm making this kind of sparse already here. Okay, so there were the coefficients. And the 3 came from the first 3 came from the term above and the one before that. And the next 3 came from the term above and the one before that. So these pink arrows are representing this relationship here, that if you want to get to the a to the m, b to the n terms, you have to look at the a to the m minus 1, b to the n terms above, and you'll get all of those, and then also the a to the m, b to the n minus 1, and you get all of those. And so what you do is you add up these two, and you can keep going. So I'm just going to like blast through a few more. I start with 1. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then we end with 1. And then we can blast through another. It's 1, 5, 10, 10, 5, 1. Once we have that pattern, we can do these pretty quickly. And so there's the situation. So we better put a dot, dot, dot at the end. This is known as Pascal's triangle. And one of the first non-trivial computer programs I ever wrote back in the steam gauge age was to compute Pascal's triangle. It's kind of a fun thing. So anyway, so there it is, and that is these numbers here. That's giving us the coefficients because of this relationship. So now we have another way to get at that relationship, and so we have another way to get at these numbers, and we can count that all up. And so this counting really was everywhere. We started with something that had nothing to do with counting. Take a sum and raise it to the nth power. And then we count up how many different ways you can match up all the A's and the B's, or the S's and the T's, or the U's and the V's, or whatever letters you want to use. How can you match up all the ones and the ones? That's how you get 2 to the n out of this. And then you also get this relationship that goes back for a very, very long time. I mean, I think therefore I am sure this is Pascal's triangle. And so that would be Descartes, sorry. Anyway, and so let me show you one last thing that makes this very interesting to computing. And we've seen this now two different ways. If you look at Pascal's triangle, it's a palindrome, 1, 5, 10, 10, 5, 1. Or if you look at these binomial coefficients, n choose k is the same as n choose n minus k. There's symmetry here. So if you want to calculate this, you only have to calculate half. This is a big deal, and this is a big part of algorithm design to speed things up. If you realize, oh look, I have a symmetric problem, so I only have to calculate half, or some times it might be a very much smaller proportion. So noticing the symmetry gives you a way to shortcut this calculation and make it happen much more quickly. So I'm going to illustrate that with the next line of Pascal's triangle. We got 1, 6, 15, 20, and then just read that all backwards. 15, 6, 1. So I've kind of color-coded it. Anyway, you can study this more carefully on the scan, but that's the situation with counting. It really is everywhere. So it's very important to get to know how to use all these combinations and permutations.